Right, so I can get to the introduction part while everyone's settling in. So you, or most of you probably have not met me. I'm Gyorgy. I work at .gnome, same as Norby. I've been there for 4.5 years now, roughly. Started off on Java projects, then moved on to .NET, and later on JavaScript. So these days I do pretty much whatever seems useful. But that's enough introduction. Let's talk about garbage collection. So you may have noticed that there are these plastic bins on the streets, and you can put your trash in them, and eventually a bunch of guys in bright orange jumpsuits come and take it away in their fancy little dumpster, or, sorry, truck. But as fascinating a subject as that might be, that's probably not the reason you're here. So let's talk about garbage collection. In a language like Java, you only ever allocate memory for objects. The part where memory is freed, which contains unused or otherwise unnecessary objects, that is managed for you automatically. And the procedure that is responsible for doing so is the garbage collector. As previously mentioned, the JVM obviously comes with such a feature, which can be configured in various ways to use various different algorithms, which I will go into a bit later. But first, let's see what the theoretical background for all this. All of the garbage collector algorithms available in the JVM are generational garbage collectors, which operate under the weak generational hypothesis, which postulates that 1, most objects become unreachable quickly, and 2, the vast majority of references from old objects are not to newer objects. So there are a few references from older to newer objects only. As a result, we can group objects into 2 categories. One of them, which accounts for the vast majority of objects a program allocates, are going to be short-lived, and the rest, a tiny minority of the objects, will live for a long time. To make use of this fact, the garbage collectors divide the heap into 2 regions, one for the young generation and one for the old generation. Each time an object is allocated, it goes into the young generation. This part of the heap is garbage collected very frequently, because it's going to be efficient, since we expect the objects to not live for very long. If they happen to survive for long enough, they are promoted to the old generation, in which they will stay for a considerable amount of time, and so this part of the heap needs to be collected less frequently. In addition, in the JVM, there's also a 3rd region, the permanent generation, which is only useful for the JVM to store its various metadata, which you can't really access. So from the end user's point of view, its only reason to exist is to generate random permgen space exceptions. So based on the previous image already, you can see a number of tuning options. And since we haven't talked about JVM flags for about 2 minutes now, it's time to get into that. So one thing you can adjust is the new ratio, which is the relative size of the old generation compared to the young one. The performance implications of this are fairly straightforward. The larger the young generation is, the fewer times it needs to be collected. And the flip side of this is that the old generation will be relatively smaller, so the old generation will need to be collected more frequently. So you need to balance this out to some degree. Instead of specifying the ratio, you can also specify the size of the new generation directly, with a starting size and a maximum size, or just specify both of them at the same time. And the interesting part here might be that you have 2 values, one for the starting value and one for the maximum value, which points at the fact that the JVM uses adaptive sizing for the heap. And the point of this is if that your application happens to not use that much memory, it will only have to contend with a smaller heap, and therefore it will be able to scan it more quickly as well. Only if you actually do end up allocating a lot of memory will the heap expand to meet those needs. Other than the generation sizes, you can also tune the heap size as a whole. So again, here you have 2 parameters, one for the starting size and one for the maximum size. So not much really to talk about there. But you may have figured out a way to completely eliminate garbage collector pauses from your application, and that's simple, just give it an unlimited heap. Except that does not quite work out so well, because if you think about it, an unlimited heap would also take an unlimited amount of time to scan. And if you try it out in practice, you can see that while at first you do get significant performance benefits, at one point diminishing returns kick in, and at an even later point, the negative effect of having to scan a larger heap outweighs the reduced frequency of garbage collections. So how do you actually see what your garbage collector is doing and when? Thankfully, you have yet more JVM flags for that. I promise the JVM flag stuff will be over soon, so not much more to go. The most basic one is print GC, which essentially tells you that the garbage collection happened and some memory was freed, but not more than that. If you need something actually useful, you will need the print GC details flag. This can be configured with two additional flags, the timestamps and date stamps. This basically just lets you append either relative time information in case of timestamps or absolute time information in case of date stamps. Now, so this will dump a whole bunch of useful things to the console for you, but if you want to put that to a file, thankfully there's yet another flag for that. Now, this is going to be useful because after you have a garbage collector log, you can set out to analyze it with whatever tool of your choice. For example, GC Viewer looks something like this. And this screenshot, you can see both the old generation and its current use and the young generation and its current use. I'm not sure how visible it is, but basically the old generation keeps steadily climbing and the young generation is rapidly oscillating between full and empty, as you would expect. Now, in addition to retrospective log analysis, you also have some tools to monitor the garbage collection process, or at least the memory, as your application is running. One tool for that would be JVisualVM. That's a silly name, and using the Visual GC plugin. So there are a bunch of graphs here, and I will actually talk about the meaning of them in a second. Now, sorry. So you have all this data. What are the numbers you're actually looking for in this? One of the metrics that you're interested in as far as your application is concerned is throughput. That is the percentage of useful time spent versus time spent garbage collecting. So if you want to shoot through a whole bunch of data, then this is the number you're looking for. In other times, latency is more important for your application, which is a measure of how much delay the garbage collector introduces into your program. So if you have, for example, a server-client-based setup, then this might be more relevant as far as not just processing a whole bunch of requests in aggregate, but responding significant or fast enough to each specific request. Third, another important consideration is what impact the garbage collector has on your application's footprint, whether that be CPU or memory usage. So in this case, if you happen to have a finely tuned garbage collector, that works great. If you have an 8-core machine with 4 gigs of RAM, that's not going to be very useful if you're stuck on a single-core cell phone with half a gig of RAM. So this is also something that needs to be taken into consideration. Now, let's actually get started. Or now that you know what you're looking for, let's talk about how the JVM goes about achieving these things. First, some common aspects to all the garbage collection algorithms that will be shown here. As I mentioned before, the heap is divided into a young generation and an old generation. And in case of the JVM, the young generation is further subdivided into 3 spaces. Eden, which is where new objects are allocated, and 2 survivor spaces, which is where objects that have already survived the garbage collection are kept. Or at least one of the survivor spaces is going to be always empty. You will soon see the reason why. Now, the way this works is that newly allocated objects go to Eden, and once that happens to fill up, a minor garbage collection is triggered. And now I hope this works. So the first thing that happens in this case is time is stopped. Okay, it does. Meaning that all your application threads are paused, and nothing happens until the garbage collection is finished. The reason for that is because you will be moving objects around in memory. And that would mean that your program has to contend with object references becoming invalidated in the background. That's not fun. So once the word is stopped, which is where this pause gets its name as a stop the word pause, a bunch of things will happen. First, the garbage collector will go through all the objects in the young generation and check if they are still alive. If they don't, they are considered garbage and are marked for collection. Everything else is moved to either the to survivor space, which is where it gets its name from, or if it happens to be old enough, because it has resided in the from survivor space for long enough, then it will be moved to the all generation. At the end of this process, Eden will be empty, the survivor spaces will be flipped, as you can see, the other one will be unused, and the reference or the names are also changed, and the all generation has expanded by some amount. So that's the minor garbage collection part. The algorithms start to diverge when it comes to how they deal with the old generation. So I will go into that a bit more deeply. Oh, just first list the available choices, why not? First one is the serial garbage collector, which is as simple as it sounds. The throughput one optimized for, wow, throughput, who would have thought. Then the concurrent mark and sweep algorithm, known as CMS, and the garbage first algorithm, finally known as G1. All right, so let's see what all those fancy acronyms and terms mean. Now, the serial garbage collector is the simplest one. You can turn it on with this flag because, again, you need more JVM flags. What this does is pretty simple. Whenever the old generation needs to be collected, it stops the word again and does its garbage collection. By the way, if this diagram is not entirely clear, the dark gray arrows are supposed to be your application threads. The black arrows are the garbage collector threads. And the vertical bars are the stop the word pause, unsurprisingly. So once your application is paused, the old generation will be processed, which in this case is, again, quite simple. It iterates, or it walks all over the heap and figures out which objects are still alive, and everything that is not garbage is moved to the start of the heap as much as it possibly can be. Therefore, the heap is compacted this way. Now, the point of this is that you have a nice contiguous block of memory at the end, which you can allocate new objects from. And that's all I'm going to talk about the serial collector, because you're not going to see it probably too much. And the reason for that is because the throughput collector is pretty much the exact same thing, except it does all of this with multiple threads. So you have, again, the flags you need to enable this if you want. And the diagram is fairly straightforward. Now, let's briefly look at what garbage collection looks like in the logs. So if you have the various logging options enabled, you know what you're looking for now. Minor GC looks something like this. Eden has filled up, so time to do a minor garbage collection. After that's done, Eden is empty, the survivor spaces have flipped, and the old generation has expanded a bit. The log entry for this will contain a timestamp, a before and after value for the utilization of the young generation, as well as a total size of the young generation. Again, since the JVM uses adaptive sizing for the heap, this can increase over the course of your program. Next are the total, or the before and after values for the heap utilization and the total heap size. And finally, the time it took for this GC operation to complete. Now, if you notice, this is 70 milliseconds, but in CPU time, that's more like 50. So this is already using multiple threads. Now, the more interesting part is the full GC, which is named so because it also includes the minor GC. So as you can see, after all of this happens, the entire young generation is empty, and everything that's still alive is in the old generation. The log entry will show you this as well. You have the young generation being emptied, the heap utilization, or the old generation rather, decreasing. And for some reason, this also prints out the size of the permanent generation, regardless of the fact that it's not collected in a full GC most of the time, only when the permanent generation actually happens to fill up itself, which you can't really affect, but never mind. And the most important part here would be the timing again. If you notice, compared to the previous 17 milliseconds, this is a pause of more than a second. That is a 100-fold difference, and this is with 4 threads. So if your application cares about latency at all, an entire second worth of pause is probably not a very good thing. So what if there was some kind of garbage collection algorithm that tried to avoid full garbage collections from happening? And it just so happens that there is, which is the point of the concurrent market sweep algorithm, or CMS. Again, you can use these flags to enable it. And the idea behind this is that it introduces another form of operation, which is the concurrent mark and sweep phase, unsurprisingly, which, using a bunch of background threads, actually tries to clean out the old generation as much as possible. Now, the way this so-called CMS cycle works is that there are only 2 pauses, one at the start, one at the end. At the start, it identifies the root objects in the old generation, starts scanning them concurrently, so your application is still running. Meanwhile, the garbage collector is trying to figure out which objects are garbage and which aren't. And once that's done, it stops your application again to verify that despite all the modifications you may have made, it's still correct in its assumptions. And finally, it concurrently cleans out the heap. So after all this, your heap will look something like this. You will find a bunch of objects that are garbage, and then you will free them. OK, so far so good, but we end up with a fragmented heap. As you can see, unlike the Syrian throughput collector, we have empty holes all over the place. The question then is, what kind of black magic does the CMS algorithm do to concurrently compact the heap in some way? And the answer is it does nothing. It does not do so at all. If you want to compact the heap, you will still need a full garbage collection. So that is not avoidable in case of this algorithm. Now, we have introduced some extra complexity, and with that comes some extra problems we might encounter. One of them is the concurrent mode failure, which simply references the fact that if your background threads are scanning the old generation slower than it fills up, then so much for concurrent garbage collection. You still need to pause the application and do a full GC regardless. This is to some degree solvable by using more background threads to do that concurrent processing. And the other one is the promotion failure. Now, as a reminder, promotion is objects being moved from the young generation to the old generation. Obviously, this is going to be a success if there is enough room in the old generation, except in case of CMS, the old generation can itself be fragmented. So even if you have enough space, it might not be in a single contiguous block, in which case you cannot really put an object in there, and therefore you need to compact the heap again, which triggers a full garbage collection. OK, so we've talked about how the fragmentation of the old generation causes additional full GCs, which we would like to avoid. And guess what? Someone else thought that would be useful, and so they came up with G1, which is enabled with this flag. Now, the name garbage first comes from the idea that this targets garbage first. Well, what does that exactly mean? So unlike the previous algorithms, this splits the heap into several regions, around 2,000 of them more specifically. Then it will try to clean up the regions which contain mostly garbage. And the point of this is that at the end, you will be able to reclaim entire regions, not just random locations in memory. To figure out which the marked regions should be, it uses a concurrent background thread, or several of them. And once a region is freed, or once several regions are processed, whatever is left inside of them that is alive is copied to a single region, hopefully. Thereby the heap gets compacted. So that's all a bit theoretical maybe, so let's see it in action. Even a minor GC looks somewhat different here. So you can see that instead of being 3 separate blocks, you have a whole bunch of blocks, each of which are labeled with 3 different letters. E would be Eden, S would be a survivor space, and O would be the old generation. So the young generation are effectively those blocks, and once we would like to collect them, we will end up with 2 additional blocks, one for survivors and one for whatever is promoted to the old generation. And as you can see, we went from 6 to 2 blocks, so 4 entire clean blocks of memory is what we ended up with. And the nice thing is that the entire region is going to be contiguous by definition. Right. So whenever the heap starts filling up to some degree, G1 collector will start a concurrent marking phase. Its only job is to figure out which of the regions we should go after next. So those are marked with an X, and I've also circled them to be extra helpful. Notice that meanwhile the application keeps running, young GCs keep happening, so that's why the Eden has moved and the survivor spaces have changed, and I think we even got some extra blocks to the old generation. So this really is a concurrent thing and does not pause your application. Now, once we figure out which blocks we would like to free, there will be a number of so-called mixed GCs. The reason they are named so is because in addition to cleaning up some of the marked blocks from the old generation, they will also clean up the young generation. So this process is kind of piggybacked onto the young GC process. And at the end, all of these regions will be freed, and whatever remains will be moved to a survivor space or an old or added to the old generation. Right. So again, more complexity, more problems. The concurrent failure and the promotion failure is the same as it was before. Either you are not processing things fast enough in the background, or you do not have enough space in the old generation to add items to. Now, since the survivor spaces are just regular spaces as well, or regular regions as well, it can also happen that moving an item from the young generation or from Eden to a survivor space fails as well. So this is similar to the promotion failure. And the final interesting error that can happen is the humongous allocation failure. Now, due to the regionalized design of the G1 collector, it's easy to see how allocating objects that are larger than a region can be problematic. In fact, any object that is larger than half a region is considered a humongous object and is allocated to a special set of regions that are contiguous at some point. And if this happens to fill up, it's quite costly to relocate it, triggering a full GC, all that nonsense. So if you allocate large enough objects, you will piss off this guy, and he will beat your performance to shit. Now, you might imagine there are various tuning flags you can utilize here. I mean, just the basic ones are the relative size of the young generation to the old one, the maximum heap size, minimum heap size, background worker threads, amount of occupancy that triggers a concurrent collection, percentage of garbage that is needed in a region to be considered mostly garbage. And there are probably more, but the one you will need to use is actually this one. So this lets you set the amount of pause your application is willing to tolerate when it comes to garbage collection. So this is actually the output metric you're trying to control rather than indirectly affecting it through various other parameters. So that's cool. But again, similar to the heap size, you need to be sensible about this. You can't just set this to 0 and expect GC pauses never to occur. In fact, that will cause the exact opposite. Your application will do nothing but collect garbage. So the trade-off here is obvious. You can either tolerate more frequent but shorter pauses, but less frequent and longer pauses. And in closing, here's a quick comparison of the various GC algorithms we've seen. First one is the serial collector, which is simple and has the minimal overhead but does not scale very well. Then the throughput collector, which is optimized for throughput, but latency can still be an issue. Then CMS, which tries to solve the latency issue with extra background processing at the cost of additional CPU consumption, but it still leaves the heap fragmented. And finally, the solution to that problem would be G1, which at the cost of additional memory utilization, and in fact requiring a rather significant heap to begin with, that is 4 gigabytes and up to be specific, it does partial compaction of the heap as well. So that's all I wanted to talk about. If you're interested in reading more, you can read the relevant section of this book, which is where a lot of the illustrations actually come from. And if you have any questions, I would be glad to answer them.
Yeah, about this humongous allocation issue. So basically what you're saying is if you're using...
Tell it to the man.
Yes. So if I'm using G1, I shouldn't use really big integers, basically. So if I'm working with humongous big integers, then maybe CMS would be better? Or does CMS also have a similar issue?
Yeah, so the question is whether you should be using... I just can't take that seriously, sorry. So the question was whether you should use CMS if you're dealing with really huge objects, and whether that would trigger more humongous allocation failures in case of G1. The answer is I honestly do not know, but considering that they deliberately took steps to address these kinds of issues in G1, I would expect that it would also be tuned to be on par with CMS, if not better in that sense. Or maybe you just need a larger heap, and there you go.
Actually, the performance depends on the heap size you have. So below 4G, CMS will be more performant than G1 in almost all the cases. And you shouldn't use big stuff anyways.
Yeah, that's the other thing, that you should not use huge objects, regardless. Okay, someone else? All right, then we're done. Oh, no, Peter, yeah. The default depends on whatever JVM version you're using and OS and whatnot. But I believe the throughput was the default for some time, and in Java 8, the G1 is the default. Okay, well then, thank you for your time.